All right, so here's our new problem, our next problem. We're going to try to find the maximum shear at C for this odd set of loads. 3 loads, so we'll have to check 3 cases. So the first thing we need to do is find the influence line for shear at C. So let's start. I think we can probably do this one pretty quick. Shear is relatively easy. So the shear at C, and then I'll draw the X direction, and then I'll put some points of interest. That's the end of the beam, and then there's point C. We want to do that. Now remember, the way we handle doing qualitative influence lines using Mueller-Breslau is we'll assume we've got this weird-looking shearless connector, right? And we'll put positive shear on both sides. So qualitatively, how will this piece on the left move? This piece near here, will it move up or down?
Down.
It's going to move down. And this piece on the right will move up. So I'll draw that. Down, up. So that's what the influence line looks like. Now, we know this shape, or this distance is 2 meters, and this one is 6. So similar triangles tells us that this height here is to 2, as this height here is to 3. So I'm 6. So 6 over 2, that's 3. So this one's going to be 3 times bigger than this one. So I'll have 3 of something plus 1 of something. I have 4 somethings that need to add up to 1.
3 quarters and 1/4.
There you go. So this will be 3 quarters. And this will be minus 1/4. So now you can check it. You can say 1/4 is to 2 as 3 quarters is to 6. That satisfies it. And plus the total change here has to be 1. So shear are a lot easier to do because you don't have to go through all that additional calculations to find the value. You can usually figure it out just by similar triangles. And that additional constraint or condition that the change is equal to 1. So now with that said, I can just plow into my cases. So I'll start over here. We'll do case 1. And case 1 will be, I'll let the first load in the sequence go to the maximum value. Let's talk about this for just a second. I'm trying to find maximum shear, either positive or negative, right? Because in shear, I mean really in moment, we're looking for maximum values, not necessarily sign. I think you can see from the shape of the influence line that there's a lot more positive areas, and the ordinate values are larger positive than they are negative. So from that rationale, probably the positive shear is going to be bigger than the negative shear. So I'm going to go for the most positive. So when I let my structure or my series of loads move from right to left, when I stop it here at C, I'm not going to stop it at minus 1/4, which is to the left. I'm going to stop it just to the right at 3/4. So every time as I run through my cases, I'm going to let each of these loads stop just to the right of C and get the 3/4 value. Okay? If it were flipped over and I had negative 3/4 and positive 1/4, if this point were, say, shifted more to the right, then I do just the opposite. As I move from right to left, I would let this go to the left and get the largest ordinate value every time. Okay? So case 1 will be this. So again, I'll help you kind of visualize it. I will redraw it to some scale. So there's the influence line. So we'll let the first load come and sit right about there. That's the 1 kilonewton load. And then 1 meter back is the 4 kilonewton load. And then 3 meters back is the 6 kilonewton load. So that's 1 meter and 3 meters. So that's a total of 4 meters, so they're all on the structure. So I'm going to need 3 different values here. Now I know one, it's easy. This top value is 3/4. Let's check the slope of this line. So it's going to be rise over run, so 3/4 over 6. Right? So that's going to be 3 over 24, which is what, 1/8? So every meter I move to the right, my value will drop 1/8. So I did move 1 meter to the right. Right? So I'll drop 1/8. So just to get the common denominator, this 3 over 4 will become 6/8. So 6/8 minus 1/8 will be 5/8. And then I drop 3 more, 3/8. So 5/8 minus 3/8 is 2/8. So now I can put it all together. So my shear at C for case 1 will be 1 kilonewton times 3/4 plus 4 kilonewtons times 5/8 plus 6 kilonewtons times 2/8. What is that? 4.75. Anybody else get that?
Yes.
4.75, and that'll have the units of kilonewtons. All right, let's do case 2. And I will again redraw the shape to kind of give me a hand. So this time we're going to let the second force come in. This will be the 4 kilonewton force. And then 3 meters back, we'll have the 6 kilonewton force. And 1 meter forward, sorry about that, I kind of jammed that all in there. It's not very pretty. Okay, so the same slope applies for this right-hand side. So I go 3 meters, I'm going to drop 3/8. So I know this height was 3/4 or 6/8. 6/8 minus 3/8 is, what did I say? 6 minus 3, 3/8. Yeah. Now the slope of this side, well, it's 1/4 to 2, and interesting, it's the same. It's 1/8. So both these slopes are always the same in shear. Well, on these segments. So again, I move 1. I'm gonna increase 1/8. So if I started at negative 1/4, which is 2/8, this would bring me up to negative 1/8. I'll see if I can squeeze all this in over here. So the shear at C for case 2 is 1 kilonewton times negative 1/8 plus 4 kilonewtons times positive 3/4 plus 6 kilonewtons times positive 3/8. So what's that value equal to?
I got 5.13.
5 point what?
13.
Anybody else get that?
Yes.
5.13, and that'll be kilonewtons. So that case seems to be controlling right now. One more case to go. Case 3. So now our last force, which is the 6 kilonewton force, goes to the top. 3 meters forward is the 4 kilonewton force, but it's only 2 meters left, so it's off. And then the front force is a meter forward, so it's off too. That's it. So this one's not too bad. That height there was 3/4. So the final one is the shear at C for case 3 is just 6 kilonewtons times 3/4. Which is what, 4.5? So based upon this, it looks like the maximum shear at C is going to be 5.13 kilonewtons. And that took about 11 minutes to do, so that's not too bad. Any questions about that one? You guys are good.